Yes, good morning everybody. Welcome to this session of Sustainable Construction Methods. Today we'll be seeing this topic, supplementary cementing materials. Basically, with the urbanization taking place with a very rapid pace, we need to come up with some alternative where the cement can be replaced with different other materials. So different researches have been done from the past decades, and we have come up with some other materials which have performed very well when they were replaced with cement, partially or completely also. So we'll be seeing that what are the different materials that have been an alternate to the cement. Let us see this is the fly ash. Basically, what is the fly ash and all these things will be seen in detail in the further slides. Ground granulated blast furnace slag also we have, and we have silica fume, calcined shale, metakaolin. And these materials are generally categorized as supplementary cementing materials or mineral admixtures. Basically, they have performed very well when they were mixed in a proper proportion. And in the fresh concrete as well as after the concrete was hardened, different tests were performed and seen whether these concrete when mixed with these supplementary cementing materials got the desired strength or not. Let us see it here. You can see here these are the supplementary materials from the left side to the right side. You can see here. This is the first one is fly ash. Basically, what is fly ash? Class C fly ash is this is the class C fly ash, and the other one is the metakaolin. And the next one is the silica fume. Let us see here. This is the fly ash class C. Basically, in class C fly ash, what happens is the amount of calcium oxide is about 8 to 10%. And in the metakaolin, this white one is the metakaolin. Basically, what is metakaolin? Metakaolin is a product which we get from the China clay. Basically, what is China clay? Is this clay is used to make porcelain dishes, porcelain materials. So this is the metakaolin, that is metakaolin. And what is silica fume? Silica fume is that byproduct which we get from the thermal power stations. When the coal is burned, the byproduct which is left, that is silica fume. And class F slag, this is also fly ash, but it has the content of calcium oxide is different when compared to class C fly ash. And calcium shale, this is the last one, this is the calcium shale. This is also a byproduct which we get when from the aluminum alloys when they are burnt, or the other alloys which are burnt. After that we get this cementing material. Let us see the next slide. You can just see, here we are comparing what is the difference between the other cementing materials and this Portland cement. You can see here, here there is a chart here. As in this Portland cement, silicon dioxide is 21%, and you can see fly ash class F is 52%. So you can just see here, 52% is silicon dioxide, and in class C fly ash you have 35% of silicon dioxide. So this is important here. Silicon dioxide is 21% in Portland cement. In class F fly ash it is 52%, and in class C fly ash it is 35%. Slag cement it is 35%, and in silica fume it is about 85 to 97%. So this is the difference. Here we have aluminum oxide. In Portland cement it is only 5%, whereas in class F you can see in class C fly ash it is 23 to 18%. So this is the difference what we have in the chemical composition of these different cementing materials. This is the difference. You can see in aluminum oxide we have Portland cement, it is only aluminum oxide is only 3%, whereas in class F fly ash it is 11 plus, and class C fly ash it is 6%, whereas in slag cement it is only 1%, and silica fume there is no content of aluminum oxide here. And next, this is calcium oxide. The main content, the main percentage of calcium oxide is maximum in Portland cement, that is 62%. You can see here this is getting replaced with different things here. 62% is getting replaced with only 5% of calcium oxide, whereas that is being compensated with 52% of silicon dioxide. So this is what the changes are taking here, these chemical compositions react together and form other cementing materials which have performed very well when mixed in fresh concrete as well as in hardened concrete also. You can see a calcium oxide is very less here also of 21% when compared to your Portland cement, that is 62%, and in slag cement it is 40%. Here you can see it is only less than 1%, So Silica Fume, the calcium oxide content is very much low, but still it performs very well up to some percentage. That we'll be seeing in the further slides here. You can see the fineness as surface area is 370 kg per meter cube and 420 for class F fly ash. Class C fly ash also it is 420, and for slag cement it is 400, whereas for silica fume it is 15,000 to 30,000 kg per meter cube. So this is how the surface area it covers the surface area. Next you can see the specific gravity. Specific gravity of Portland cement is about 3.15 only, whereas in class F fly ash it is close to this range, that is 2.38, and even in class C fly ash it is 2.65, relatively close to your specific gravity of Portland cement, and here in slag cement it is 2.94. So basically these properties are also close to the Portland cement. Their specific gravity is also close to it. Here you can see in Portland cement, this is the primary binder. This is used, cement is used is the main content which is used in the concrete, whereas here fly ash of class F is of cement replaced. It can be replaced to some percentage. As I had told you, that percentage will be seen in the next slides, and here also this can be replaced. It can't replace the cement completely. Here we'll have to see this here. The whole fly ash of class C or class F can't be replaced completely. It can be replaced in some percentage only. So that percentage, what is the best percentage? Different research have been done from many decades, and they have come up to one perfect percentage which has been very useful, and it is being used in a very huge quantity. Cement replacement also, slag cement can only be replaced, and here it enhances the property. Silica fume is used when we want to enhance the property. Sometimes what happens, we want to add some admixtures where we can reduce the water content, or we want to increase the workability. At those times this is also very much useful here. So this is how the chemical composition of different cementing materials is placed here. Let us see the next slide. Now cementing materials are added to concrete as part of total cementing system. So basically they are added. Why do we want to come up with different cementing supplementary cementing materials? Is as the construction is taking place at a very rapid pace, and everybody wants to come up with good houses in rural areas as well as in urban areas. So we need to come up with some other materials which can reduce the amount of natural resources, because with this rapid demand, the natural resources are getting dried up. So we need to come up with some other materials also which are waste products or the byproducts of different other products. So they may be used in addition to a partial replacement. As I had told you, they can be used as addition, or partial replacement also. Sometimes I told you either they can be used to some extent, not to full extent. Partial replacement of Portland cement, you can see here only partially. This is important here. You can't replace it 100%. Up to some content you can replace. So it can be added, or it can be replaced partially of Portland cement or blended cement in concrete, and depending upon the properties of the materials. Depending on the properties of materials also, we need to see which type of cementing material can be added or it can be replaced. That can be seen here. Let us see here, as I had told you, what is fly ash. Now let us see what are the different cementing materials. They are byproducts of which materials. Let us see that here. It is one of the byproducts of burning coal from electric power generating plants. You can see here it is from electric power generating plants, with huge coal being burned up to generate very big capacity of electricity. There what happens, the waste material that is got, that is the fly ash. from the burning. So this fly ash is from the electric power generating plants. Basically what before this research, this fly ash was waste and it was just a debris. So with this research, this fly ash, which is in huge content, is very effectively used in construction of buildings also. Upon ignition in the furnace, most of the volatile metal and the carbon in the coal are burned off. Most of the main material is burned off, and this is the leftover product. So fly ash is the leftover product. Let us see, most of the fly ash particles are solid spheres and some are hollow spheres. Most of them are solid spheres also. You don't get them in a powdered form. Most of them in a solid sphere. Then again they are broken up into a small particles. The particle size of fly ash vary from less than 1 microns to more than 100 microns. This is important here. What is the size of the particle what we get from the fly ash? It is from one, as I told you, it doesn't come in small particles size. They come up in small small spheres, solid spheres. Then they are broken up, then they are powdered into size of this 1 micron or more than 100 microns, with the typical particle size measuring under 20 microns. Basically typical particle size is below 20 microns. So this particle size is very good, which we can use it in the composition of making a concrete. The surface area is typically 300 to 500. You can see a surface area it covers is 300 to 500 kg per meter square. Let us see here, this is the fly ash. It resembles, this is the color of the fly ash. It is brownish in color. It resembles cement, and it has been used in concretes in 1930s. You can see here, it is being used in concrete 1930s. We have fly ash bricks also. Different fly ash bricks are also made, and they have performed very well when they were used instead of red bricks or concrete blocks also. They have performed very well. So this is the fly ash. And this is with the microscope, when we check this fly ash, you can see a scanning electron microscope, micrograph of fly ash particles. You can see although most fly ash spheres are solid, some particles called cenospheres are hollow. Some of them are so hollow. As I have told you, all the particles are not in a powdered form. They are in some solid form, and some of them are hollow also. You can see here, they are hollow. They have air voids in it. Once these particles are powdered, then we get the size of the fly ash as we wish. That is most of them are less than 20 microns here. So you can see here, this is after it was done, scanning electron microscope was used and seen how the size of the fly ash was. Let us see the class F fly ash. What is class F fly ash now? Class F fly ash are low calcium. That is less than, you can see it is less than 8% calcium oxide. As I had told you, the content you must, hope you can remember in the previous slide, in Portland cement, the content of calcium oxide was about 62%. Whereas here, the content of calcium oxide is less than 8%. So this is class F fly ash. Class F fly ash, the calcium oxide content is very low. Fly ash with carbon contents less than 5%, but some may be as high as 10% also. So maximum the calcium oxide content in class F fly ash is about high as 10%, but not greater than 10%. Now let us see the class C materials have higher calcium contents than class. So class C has higher calcium content than class F ashes. So a little difference here, the calcium oxide content is a little bit greater in class C fly ash. The class C ashes generally have carbon contents less than 2%. Less than 2%, many class C ashes when exposed to water will hydrate and harden in less than 45 minutes. This is very important here. What happens when we mix different materials in concrete? The other property what we have to check is what is the time they take to harden. Sometimes what happens when we are constructing in a region where it is a very cold region, there at those places we need to see how much time does these materials take to harden up. Because if they take a lot of time, then the property or the strength what we desire to achieve, that is not achieved here. So this class C is very good in hardening up. It takes only 45 minutes also, 45 minutes. So this is also a very good aspect which we have have got, the class C performs better than class F fly ash. Let us see here. In the next slide, what is now, this was with the fly ash, class C and class F fly ash we have. The basic difference between both of them is they have the calcium content is different in both of them, and both of them perform very well, but a slight difference in both of them are the class C fly ash hardens in about 45 minutes only, whereas the class F fly ash, it takes some time. Let us see what is silica fume. It is also referred to as microsilica or condensed silica, microsilica or condensed silica fume. It is a byproduct material that is used as a pozzolan. So this is a pozzolan. It is used as a, now what is this? This byproduct is a result of reduction of high purity quartz with coal in an electric arc furnace. So this is a byproduct which we get when the coal is burned with quartz in electric arc furnace. So basically, when in electric arc furnace, when different materials are being manufactured at those places, what happens when the coal is burnt with high purity of quartz, then the byproduct what we get, that is this silica fume. And electric arc furnace in the manufacture of silicon or ferrosilicon alloy. So when they manufacture silicon or ferrosilicon alloy, at that time the byproduct which we get, that is the silica fume. This is huge amount of electric hard arc furnaces. They are very huge and they generate a lot of silicon and ferrosilicon alloy. So the byproduct which after the burning of coal and high purity quartz, this is the silica fume is the byproduct which we get. Let us see what is the properties of this silica fume. The condensed silica fume is essentially silicon dioxide. See, what is it? What is it? It is essentially silicon dioxide, more than 85%. We must have seen in the chart in the previous slide the 85% of silicon dioxide, whereas in Portland cement and other cementing material, the silicon dioxide content is not such high, whereas compared in silica fume. So here the maximum amount of percentage is silicon dioxide in silica fume. Since it is airborne material like fly ash, it has a spherical shape. The shape is also spherical. In fly ash also the shape was spherical. It was also spherical in size. It is extremely fine with particles less than 1 micron. You can just see this. This is important here. The size of the particles. See, we just can't use any cementing materials which have high particle size. It has to be crushed. But the minimum size, what do we get after crushing? After it has been powdered, what is the size we get? That is important here. In silica fume, the size is about only less than 1 micron in diameter, and with an average diameter of about 0.1 micron. You can see this is very good. The size of the particle is very fine here. The more the finer, it will be very easy. It won't have voids in it. This is the benefit what we can achieve because of the size of the particle here. About 100 times smaller than average cement particle. You can just see here it is 100 times smaller than average cement particles. Now what we'll have to see is, though this has been achieved, the particle size is very good. It is very lesser than the cement particle size also, Portland cement particle size. But how does it perform? That is to be seen here. Let us see here. This is the silica fume powder. It is black in color. And you can see the particle size is very, very fine. It is 0.1 microns. It is 100 times lesser than Portland cement particle. Let us see here, when it was taken with scanning electron microscope, the silicon particle fume at 5,000. You can see here, you must have, I hope you can remember in the previous slide, the size of the particle in fly ash was spherical, and it was hollow also from inside, whereas you can see it is so fine you can't see the spherical size also here. Spherical size can't be seen here with a high intensity microscopic micrograph also. You can't see the size also. So it is very fine. So very fine particle. It is very good. It is when mixed with other materials, how does it perform? We'll see it here. Let's see, silica fume is used in amounts between 5% and 10% by mass of total cementing material. So here what is important here, it is used only in about 5% to 10% only. So it can be it can be replaced partially. It can't be replaced completely. It can't replace the cement completely, but only 5 to 10% of whatever cement we have used, it can be replaced with 5 to 10% only. It is used in applications where a high degree of impermeability is needed and in high strength concrete. So where as I told you, the size of the particle is very small. So what the advantage of this is it can be used in places where high impermeability is needed, where places where there is drainage system and a lot of water flows from there. At those places, this silica fume can be used because it is very good in impermeability. It doesn't let anything flow through it. It is impermeable and it is high in strength also. With mixing of silica fume in the concrete, high strength is also achieved. So these are the advantages with the silica fume. You can see here where it is used. Although they can be used in general construction, silica fume and metakaolin are often used in applications such as bridges and parking garages to minimize chloride penetration into concrete. Chloride penetration. You can see here the biggest advantage of silica fume is, see where it is used. You just see here, it is used in applications such as bridges. Bridge is a very important structure. There you can see here, bridge is a very important structure. It is most of the time or sometimes it is constructed at a place where there is a river or a water body flowing from there. We want to give a passage to the traffic, and there this silica fume is used in these constructions, bridges as well as in parking garages to minimize chloride penetration. As I had told you, it is used in places where we need impermeability, we need maximum impermeability. So the chloride also can't react and can't penetrate into this type of concrete. So at these places it is very much feasible and very much beneficial also. So you can see bridges and as well as these parking areas also. Bridges is a very important structure. A lot of traffic goes through it, and these are constructed especially at places where there is no proper link to connect from one side to the other side. At those places bridges are constructed, as well as at those places where the traffic is very much congested. At those places bridges are constructed, and in that bridges this silica fume can be used here. You can see here, let us see what is the third other cementing material. It is slag, ground granulated blast furnace slag, also called as slag cement. It is made from iron blast furnace. You can see it is made from iron blast furnace slag. See, most of these are byproducts only, used in different industries. When the coal is burnt mixed with different other materials, the byproduct what we get, this is the type of this is the one of the byproducts which we get from after burning from the coal. Let us see, it is a non-metallic hydraulic cement. It is non-metallic. It doesn't contain any metals in it. It is non-metallic hydraulic cement consisting essentially of silicates. It consists of silicates and aluminum silicates. You can see both these, it consists of both of these silicates as well as aluminum silicates of calcium developed. Where it is developed in a molten condition simultaneously with iron and blast furnace. It is developed in a molten condition. It is developed in a molten condition with simultaneously with iron and blast furnace. So basically this is developed in a blast furnace in a molten form. After it is being cooled and dried, then we powder it. Then this slag is used as a supplementary cementing material. Even this performs very well. Let us see what all it contains and how does it perform here. You can see here, this is the slag. This is a slag. It is the size of this slag particles are very a little bit more bigger than fly ash and as well as the cement slag also. So the size of particle is a little bit silica fume. The size of the particle is more bigger than silica fume and fly ash class C and fly ash class F. This particle size relatively it is bigger. Let us see the molten slag at a temperature about 1500 degrees Celsius is rapidly cooled. It is rapidly cooled by quenching in water to form a glassy sand like granulated material. So basically this is got in a molten form. It is cooled rapidly by quenching in water. After that, what happens, when it cools down, we get this glassy sand like granulated material. We get this material in a granulated form. Now what do? The granulated material which grounds to less than 45 microns. You can remember the silica fume, the size of the silica fume was about 0.1 micron, which is 100 times lesser than Portland cement, and the size of the particle in class C fly ash and class F fly ash was about less than 10 microns to 10 microns, but here the size of the microns is 45 microns. So the size of the particle size relatively it is bigger in silica fume as well as class C and class F fly ash. The surface area fineness is about 400 to 600. You can see here the surface area what it covers is about 400 to 600 meter square per kg. In 1 kg, about this 400 to 600 meter square the surface area it can cover. So basically the particle size are relatively high, so this slag can be used in some content. Let us see the other materials. What do we had? Natural. Now these were the byproducts. Till now what we have seen, these were byproducts. Now let us see what is the natural materials do we have, other natural materials which can be used as a replacement in cementing material. So natural pozzolans have been used for centuries. So these have been used for centuries. Many of the Roman, Greek, Indian and Egyptian pozzolan concrete structures can still be seen today. You can see here many structures which were built about many centuries beyond also. Even still those structures have they still have a very good strength, they still perform very well. So what were used in those structures was this natural pozzolans. Let us see what are those now. The most common natural pozzolans used today are processed materials which are heat treated in a kiln and then ground to a finer powder. So basically these natural materials are first taken, they are heated in a kiln and then they are finely powdered. So basically we don't get them in a very powdered form. We'll have to heat it, we'll have to then get it into some smaller particle, then we powder it, then we use it as per our requirement. So those are calcium clay, one of them, calcium shale and metacolumn. See, these three have performed very well. These were natural minerals, but they had to be treated and changed into different form which could be used. Now let us see. Till now we have seen the different cementing materials which can replace cement. Now what is important here? We have got this. Let us see now how do they perform when poured in fresh concrete and how do they perform when after this concrete has been hardened up. Let us see effects on freshly mixed concrete. Concrete mixtures containing fly ash generally require less water. You can see here they require less water, that is 1 to 10% less for a given slump than concrete containing only Portland cement. See, this is the benefit what we have achieved here. The water content has been reduced because of after adding the fly ash. So this is the water requirements that has reduced here. If you calculate this water requirement in very big huge areas, this is a very beneficial advantage here. Similarly, ground slag decreases water demand by 1 to 10% depending upon dosage. See, even this has been very helpful in reducing the water content also, ground slag. The water demand of concrete containing silica fume increases. Here the water demand of concrete containing silica fume increases with increasing amounts of silica fume. As we increase the silica fume when mixed in concrete, the water content is increasing here, whereas in fly ash and in slag the water content is decreasing to 1 to 10%, and here the water content is increasing when we increase the silica fume. Unless water reducer or super plasticizer is used to overcome this problem, we can use super plasticizers. What does super plasticizers do is, when super plasticizers are added into the mix, they reduce the water content. So we have different options also to overcome this problem. Let us see the workability. So what is workability? Basically workability is the ease with which we can mix the concrete and place it. and spread it. So that it should have that ease also. We have mixed different materials, but the concrete is not in a position which it can't be mixed easily, or it can't be placed easily. So this also problem has to be seen. So workability, let us see how do they act in terms of workability. The fly ash slag and some natural pozzolans generally improve the workability of concretes of equal sum. See, this is a very beneficial factor here. So the workability is getting increased because of usage of slag, fly ash and silica fume also. So even this is being achieved because adding that. Normally what happens when different other materials are added, the workability decreases, and because of that what we'll have to do is we'll have to add some super plasticizers to overcome that problem. So while silica fume may reduce the workability, it can reduce the workability and contribute to thickness of a concrete mixture. But the silica fume, what happens, it can reduce the workability, but no problem, because silica fume is available in a very high quantity. We can use that silica fume and overcome this problem of workability by adding super plasticizer. So let us see the next, bleeding and segregation. Now what happens when different materials are added? If the proper mixing doesn't place between those materials, then there are chances of bleeding and segregating of different materials. We'll have to see when we are when we are replacing different materials to replace cement, we have to see this thing also, whether they can, how do they perform in terms of bleeding and segregation. We'll have to see this also. Due to reduced water demand, concretes with fly ash generally exhibit less bleeding and segregation. You can see a reduced water demand. Concretes with fly ash generally exhibit less bleeding and segregation than plain concrete. See what is happening, because adding these materials, the water content is getting reduced. Because of that water content getting reduced, even the bleeding problem and the segregation, this is also overcome here. We can overcome this also. So this is the benefit of adding different other cementing materials. Let us see how does the ground slag perform. The ground slag with similar fineness as cement, as the fineness is basically same as that of cement, may increase the rate and amount of bleeding with no adverse effect on segregation. A little bit of bleeding takes place, but segregation is not there. The materials don't segregate. A little bit of bleeding does take place. The water moves away, but the different materials don't move. The mixing is very proper here. So this also performs very well. The ground slags also perform very well. Ground slags finer than cement reduce bleeding. So here what we'll have to do is the particle size of ground slag, that has to be reduced. If that particle size is reduced, then it performs very well in terms of bleeding also. So in terms of bleeding and segregation also, these different cementing materials perform very well. Let us see the setting time. Now we'll have to check this also. After the concrete has been poured, different materials have been mixed and concrete has been poured, the setting time also has to be checked. It should be lower. The setting time also should be lower. If the setting time is increasing, then we will have problems at some places where the setting should take instantly. Fly ash, ground slags and natural pozzolans will generally increase the setting time. See, even in terms of setting time also, the setting time is also increasing when we are adding these materials. Setting time of concrete, silica fume may reduce the setting time of concrete. So silica fume, sometimes it reduces the setting time also. Even this can be overcome by adding the different materials where the setting time can be reduced here. So in terms of setting time also, these different materials perform very well. Let us see now about the curing. How about curing? Concrete containing supplementary cementing materials need proper curing, whereas normally the concrete needs curing, but when different other materials are used, the curing should be proper. Curing is very important here. The curing should be properly done. Need proper curing. The more care should be taken in terms of curing. The curing should start immediately after finishing. The time shouldn't be lost. Once the element has been constructed or the structure has been constructed, the curing should start immediately without wasting time. This care should be taken. A 7-day moist curing or membrane curing should be applied. Basically in structures what we do is, Basically what we do is in structures, like when we construct the columns, we cover this column with a wet membrane, wet cloth membrane, you can see. So 7-day moist curing of membrane should be applied. So this is very much important here. We shouldn't neglect this, care should be taken here. Some organizations specify at least 21 days of curing for all concrete containing pozzolanic materials. So this is important here, 21 days. So even this can be done here when we are replacing such amount of high content of different materials which is being replaced with cement. So this care should be taken. 21 days of curing will be sufficient here. Let us see what about the effects on hardened concrete. Now till here we had seen how does these different supplementary cementing materials perform when mixed in fresh concrete. Let us see after this concrete has been hardened, what is the strength and different properties are achieved here. Let us see effect on hardened concrete. Strength, this is the main parameter which we have to check here. So all supplementary materials contribute to strength gain of concrete. So this is the most important property that should be achieved here. Strength, that is the basic requirement what we need. So they contribute, the supplementary materials contribute to the strength gain of concrete. So they contribute, the strength is also increased here. However, sometimes what happens, the strength of concrete containing these materials can be higher or lower with only cementing materials. Here what happens is, if proper curing is not done, if proper care is not taken, proper admixtures or super plasticizers are not mixed, then sometimes the strength can decrease. But most of the time, if this care is taken, then the strength is also increased when these different cementing materials are mixed here. Let us see. You can see the strength gain can be increased by one of the combination of the following. Now to increase this strength gain, see different materials perform differently. So to increase this strength, what we'll have to do is increasing the amount of cementitious material in concrete. We'll have to increase the amount of cementitious material in concrete, adding high early strength cementitious material, high early strength. In some materials we can high early strength is gained, so those materials can be added here. Decreasing the water content ratio, as I had told you, the water content ratio can be decreased by adding different plasticizers here. So this also can be done. Increasing the curing temperature, the curing temperature also should be increased. As the curing days are increased from 7 days and 21 days, a proper care should be taken that this is done completely with the specific days as mentioned here. And the curing temperature can be increased using an accelerating admixture. So admixture, it can accelerate the hardening of concrete and different other properties also. If these things are added, incorporated in our mix, then the strength can be increased here. Let us see how it performs in permeability and absorption. We have to see, is this concrete permeable or impermeable. We'll have to check that also. With adequate curing, the concrete with supplementary materials will reduce the permeability and water absorption. See, if the curing is proper, the permeability and the water absorption, both of them are reduced here. It performs very well in terms of permeability and absorption. Silica fume and other pozzolanic materials can improve the chloride resistance under 1000 coulombs using AS steam. This is a test. This is basically a test to see how does it perform when with chloride resist. Does this cementing material, do they resist chloride attack? Do they resist chloride effect on the material? This can be checked with this test. So it performs very well in terms of permeability and absorption also. Let us see sulfate resistance, because the concrete structures are constructed in places where there are water bodies also. In those places what happens, there is sulfite attack also on this concrete, thereby they weaken the structure, they weaken the reinforcement which is inside. So we'll have to see whether this supplementary materials, can they resist this sulfite resistance or no. The sulfate and seawater, you can see a seawater damaging effect on concrete can be reduced significantly. It can be reduced significantly by using silica fume, fly ash and ground silica. You can see here it is very good. These structures which are constructed in water bodies also can be constructed using these materials, silica fume, fly ash and ground slag, where they are performing very well against the sulfite attack also. The improvement can be reached by reducing the permeability and reducing the reactive materials such as calcium needed for expansive sulfate reaction. So it can be improved by reducing the reactive materials such as calcium. So the reactive calcium reacts with sulfide. If this calcium content is reduced, then it performs very well in terms of sulfite resistance also. This calcium content has to be reduced, because when calcium and sulfide they react each other, then it might cause damage to the structure here. So it performs very well when in terms of sulfate resistance also. Let us see corrosion of embedded steel. Now we'll have to check, does this resist the other attacks which come onto the concrete? Does these materials resist the corrosion also? The improvement in corrosion resistance of concrete can be achieved by reducing permeability. It can be achieved by reducing permeability. If permeability is reduced, if there is no water seeping into the concrete, then simultaneously this corrosion also will be decreased, increasing the electrical resistivity of concrete. If the electrical resistivity of the concrete is increased and the permeability is decreased, then this can it can resist the corrosion also. Fly ash can reduce the permeability of concrete to water, air and chloride ions. See, it can reduce the permeability of concrete in water, air and chloride ions also. Silica fume greatly reduce the permeability and increase the electrical resistivity. You can see silica fume is increasing permeability and reducing permeability and increasing electrical resistivity also, which was our need. So it performs, these things perform very well in terms of corrosion also. They reduce the corrosion of steel to a very good extent. So these were the properties and these were the different cementitious material which have been replaced with cement in different percentages, and they have performed very well in terms when they mix in fresh concrete as well as when after the concrete was hardened. Different checks had been done and different checks had been done and they have performed very well in it. So different tests were performed and they performed very well in terms of hardened concrete also. So thanks a lot for this session. I hope it was informative to you. I request all of you all to please go through this session, and if you have any questions, you can comment in the comment section. Thanks a lot. Thank you.